Hi, I'm Hu Zhenxi. I'm going to present you our research, GFIE, a dataset and baseline for case following from 2D to 3D in indoor environments. Case following requires inferring where the person, in a sense, is looking. However, a survey of datasets used for case following tasks reveals defects in the way they collect case point labels. So, we first present two key problems. To address the problems mentioned above, we developed a system to record case behavior and released the novel GFIE dataset with reliable annotations. We also proposed the baseline method for improving case following. Some test samples on the GFIE dataset are given for an overview. First, we state the motivation for this study. We conducted a survey of datasets used for case following and found defects in the way they collect case point labels. Most datasets are manually annotated, but the subjectivity of annotators may cause annotations to deviate from the actual case target. In addition, label-intensive is another drawback. The eye-tracking device can capture annotations automatically, but alter subject's appearance in the dataset. It may bridge the gap with the case-related behavior in the nature environment. In this work, we propose a novel system for establishing our GFIE dataset, and we use the laser spot emitted by the laser rangefinder to guide and locate the case target. After collecting various case behavior, accurate annotation can be provided for establishing GFIE datasets. In addition, we introduce a stereo field of view in the proposed baseline method for improving case following. These are our main contributions. Next, we briefly describe the workflow for GFIE dataset generation. The case data collection system consists of a laser rangefinder and an RGBD camera, or the Kinect. Or the Kinect is set to capture RGB and DIPS images. Laser rangefinder are used to measure distance while emitting laser light. Then we can operate the laser rangefinder to guide the subject's attention target through the laser spot. The subject is always staring at the laser spot while performing in front of the camera. After collecting various case data, we need to build a workflow to generate the GFIE dataset. There are three key steps here, including laser spot detection, laser spot elimination, and annotations generation. We first propose the CVPR algorithm for laser spot detection. Then we use existing image inputting algorithm to eliminating laser spot. Our GFIE dataset provide annotations including head bounding box, eye locations, and gaze targets. The first two are generated by detectors, where the gaze target can be obtained based on the detected laser spots, camera intrinsics, and mirrored distance. Failure cases in annotations were manually checked and corrected. These two demos are examples of laser spot detection and eliminating laser spot. In the video on the left, the detected laser spots are in the red bounding box. The GFIE is a multimodal dataset. It consists of over 70,000 frames and contains various case behavior of 61 subjects. The dataset split are shown in the table. Statistics from 2D plane to 3D space are also shown in the figure. Some things in the GFIE dataset are displayed here. We also propose the GFIE baseline model. It consists of three key components. One module is used to estimate case direction. Based on predicted gaze direction, the model that perceives the stereo field of view is proposed to highlight regions that a person pay attention to in space. Then, we can infer gaze targets based on the module for generating gaze heat map. A strategy for 3D gaze following is also designed to extend the proposed baseline to infer gaze target in 3D space. In the experiments, some gaze following and gaze estimation methods are introduced for comparison. Our proposed method achieves the best performance on the GFIE dataset, both in the 2D and 3D scenes. In addition, ablation studies also demonstrate the effectiveness of our proposed method. Here is the performance of the proposed baseline method on the GFIE dataset. The red line in the point cloud represents the ground truth, while the green line represents the sight line predicted by the GFIE model. Here are two other cases. We also did a cross-dataset evaluation on the CAD 120 dataset. This is our study. Thank you very much.